So in chapter 10, we're going to move on to two samples instead of doing a one sample confidence interval or a one sample significance test. We're going to do two sample intervals and two sample significance tests. And we're going to start with proportions. And the reason why we would do this is if we want to compare our effectiveness of treatment 1 and treatment 2. So I have a completely randomized experiment, and I've got two different treatments. The TX is your abbreviation for treatment. And I have two different treatments, and I want to know the effectiveness of each one and compare those to one another. So this is why I would use these tests. Okay? When I'm using these, when I'm talking about proportion, I'm going to have P1 and P2, and both of those will stand for successful outcomes for each of the different kinds of treatments. So our P1 would be the successful outcomes for treatment 1, and P2 would be our successful outcomes for treatment 2. And then based on that information, I can do inference about the difference of P1 minus P2. And just a reminder that this is what our notation would look like for this. Okay, where we have our population or our treatment. Remember, we will use the same notation before. We'll just have the subscripts of the 1 and 2, where a plain P would be our parameter, P hat would be our statistic, but this time, because we're going to have two samples, we're going to also have N1 and N2 for sample size 1 and sample size 2. So before we get started in the actual calculation of the confidence interval or the significance test, let's take a minute to relook at sampling distributions and the sampling distribution of the difference between the two populations. So what we have here is some sampling distributions from an example based on some schools, and they were asking at these schools about they were trying to determine the percentage of people that had done their homework the night before. And so we've got one school where they took a sample size of 100. Okay, and so then we've got a second school where P, our parameter here is 70% of them turn in their homework. And then the sample proportion from the second school was a sample size of 200. So there were 200 people at the second school in each sample, but their parameter was 0.5. And remember, these are sampling distributions. So what we have on each one of them, like here in graph A, okay, are 1,000 different samples. So they took 1,000 different samples of 100 people from this school, and they used the software, and they got an approximate sampling distribution of P hat for 1. They did the same thing for P hat 2. Okay, so for our second school, and this one had a P for this school was 0.5, which you'll notice is where the mean centers around, is around the P value. And then they took a sampling distribution here of, that's what our third one here is of the P1 minus P2, the difference between the two. So let's focus here on sampling distribution of P1 first and then P2, just some reminders of what's going on there. Okay, so for both of these sampling distributions, we can say that the shape is approximately normal. Okay, and we get that approximately normal. Okay, we're looking at the distribution, but we're also doing our large counts here, right? N times P, so 100 times 0.7 is 70, which is greater than 10. N times 1 minus P for this particular school is 30, which is greater than 10. My sampling distribution of P2, okay, where I took a sample of 200, but I had a parameter of 0.5, gives me 100, which is greater than 10, followed by, again, 100, which is greater than 10. My center here should be centered around the mean of, basically should be the parameter. So the mean is equal to my parameter. Okay, and then my spread here, okay, and so my spread here is going to be my standard deviation using the parameter. So for the first school, I get a 0.0458. And for the second school, I get a 0.0354. And so these here are just looking at these first two, graph A and graph B here. So now let's look at the sampling distribution of P1 minus P2. Let's look a little bit closer at that one. So let's look at what's going on here with this sampling distribution, again, over here at graph C. So our shape here is approximately normal, and what you'll notice here is we just did our large counts rule. We just did it for both samples, right? We did it for sample 1, and we did it for, here's sample 2 right here. We did it for sample 2, and we made sure both of those were at least 10, so we get that approximately normal distribution. Okay, our center is going to be the mean of the sampling distribution, which is going to be P1 minus P2. In this case, it was 0.7 minus 0.5, which will give us 0.2, and you'll notice that's where our mean is centered around there. Our spread is my standard deviation of the sampling distribution, and this, I understand that this is counterintuitive. You can go back and look at kind of all of your math rules for transforming data and that kind of thing, but you're not going to subtract the two standard deviations. Yes, I am looking here at the difference between those two proportions, but when I am calculating their standard deviation of them, I'm going to add those two standard deviations as long as I meet my 10% conditions, right? And so basically what that means, okay, is that this is going to be equal to my standard deviation of, oh, I want it right, P1 minus P2. Okay, and so I'm going to add the two together. And so what this means is that my difference in the sample proportions of students who did their homework, because remember this is what this question is all about, is what percentage of students did their homework that night. So the difference in the sample proportion of students who did their homework, so that's this P hat 1 minus P hat 2, at the two schools will typically be about this far apart, whatever that's going to be equal to. Okay, it will be about this far apart, okay, about this far from the true difference in proportions, not apart, from the true difference in proportions. Okay, so my difference in my sample proportions, okay, at the two schools will typically be about that far away, the standard deviation there, from the true difference in proportions. Okay. All right. Okay, let's run through this example that looks at sampling distributions and describing them. So your teacher brings 2 bags of colored goldfish crackers to class. Bag 1 has 25% red crackers and bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes an SRS of 50 crackers from bag 1 and a separate SRS of 40 crackers from bag 2. Let P hat 1 minus P hat 2 be the difference in the sample proportions of red crackers. So part A wants to know the shape of my sampling distribution. And how do I know that shape? Well, if I take my two samples, if I do my large counts for both samples, I can help determine my shape there. So if I do my first sample size was 50 times 0.25, okay, which gives me 12.5. So that would be my sample size 1 times P1. And then I would also need to do 50 times 0.75, which is 37.5. That would be my N1 times 1 minus P1. But then I also need to check that for the second sample. Well, the second sample only had 40 crackers, but it had a proportion of 0.35, which is going to be equal to 14. So that would be my N2 times P2. And then I would need 40 times 0.65, which is equal to 26. That would be my N2 times 1 minus P2. All of these are greater than or equal to 10, so I know that my sampling distribution here is approximately normal. Okay, and so for part B then, it wants me to find the mean of the sampling distribution. So to find the mean of the sampling distribution, I'm going to, my mean of P hat 1 times P minus P hat 2 is equal to my parameter, my first parameter minus my second parameter, which in this case then is 0.25 minus 0.35, which is negative 0.10. And then my last one asked me to find the standard deviation of the sampling distribution, and again to show my work. Well, what I have going on in this last one here is I need to make sure that my 10% conditions are met, and they're met because I'm told right here that each bag has more than 1,000 crackers. And so I have 50 times 10 gives me 500, and 40 times 10 gives me 400, but it told me each bag had a population bigger than 1,000, which means my sample sizes then are less than 10% of my population. So I can then calculate my standard deviation of p hat 1 minus p hat 2, and that's going to be equal to, all right, let's see if we can make this not super messy. That's going to be equal to my p1, which is 0.25, times 1 minus p1, which is 0.75. This is over my sample size of the first one, which was 50. That would be my standard deviation of the first bag, plus the standard deviation of the second bag. So 0.35 times 1 minus 0.35 over this time a sample size of 40, which is going to give me 0.0971. And again, what that means is that my difference in the sample proportions of the two bags of crackers, in particular looking for the red crackers here, will typically be about 0.0971 from the true mean difference in the proportions, from the true difference in the proportions, the true difference in the proportions. Okay, so let's look now then at constructing a confidence interval about the difference in the two proportions. So this is very, very similar to if we just had one proportion. I am going to show you right away how to do this on the calculator, so that hopefully we don't mess up too many of our numbers as we are manipulating things. But you need to remember you have got to do the same 4-step process that we've been doing: the state, the plan, the do, and the conclude. And so because you have to do all of those things, one of the things you're going to need to do is check your conditions. And so our conditions, when we're constructing a 2-sample, okay, or a confidence interval about differences in proportions, we basically have our exact same conditions. It has to be random. Okay, or they have to come from 2 groups in a randomized experiment. Okay, since this could come from, and we'll look at an experiment as the very last thing today. Okay, I've got to meet my 10% rule that I had to do before. Just my difference here is both of my things have to meet my 10% rule. Same with my large counts. And just like we looked at just now for the sampling distribution, they both need to meet my large counts conditions. So the same conditions we were doing before. And then the actual construction of it is the same. Okay, remember our formula for constructing a confidence interval is our test statistic. Okay, and so that's what I get here, right? My test stat, which is the difference here between my 2 sample proportions. Okay, that critical value, which we find, remember using that inverse norm. So my critical value, and then my standard error, because I'm going to be using my samples. I'm not using from my whole population. You notice I calculated it the same way. I'm still adding there, but here you notice I'm using my p hat. Okay, so I'm using my standard deviations of my 2 samples, which technically means that I'm using my standard error when I go to calculate this. And this will tell me the difference in sample proportions, how far the difference in sample proportions will typically be from the difference in the population proportion if we repeat the random sample assignment many times. So that's how my standard error is going to be different. It's telling me how the difference in my sample proportions are, how typically different those are going to be from the difference in the true population proportion if I repeat that particular sampling many, many times. Our test here is called because in your plan part you have to also name your test. So I have a 2-sample Z interval for a difference between proportions, between 2 proportions. It's a long name, and we'll work on adding this information to our summary chart that we have, but that's the name of your test there, a 2-sample Z interval for a difference between 2 proportions. So let's run through an example. Okay, let's look at what we have here example-wise. So as part of the Pew Internet and American Life project, researchers conducted 2 surveys in 2012. The first survey asked a random sample of 799 U.S. teens about their use of social media and the Internet. A second survey posed similar questions to a random sample of 2,253 U.S. adults. In these 2 studies, 80% of teens and 69% of adults used social networking sites. So part A here has us calculating the standard error of the sampling distribution of the difference in the sample proportions, teens minus adults. So you'll notice they went ahead and they defined what order they were looking at the difference. And you will need to make sure that you define that order as well. Okay, and then what information does this provide? So basically, what does this mean? So we're looking for our standard error of p hat 1 minus p hat 2. And so what this is going to give us, again, is our standard error of each one. So our first sample here was the teenagers. And so they had of my teenagers, right, my p hat 1 is 0.8. Of my adults, my p hat 2 is 0.69. So I have a 0.8 times 1 minus 0.8, which is 0.2, over our sample size. And so of our teenagers, that was 799, plus the standard error for the adults, which is 0.69, times 1 minus 0.69, which is 0.31, over our sample size of adults, which was significantly larger, which gives us a value of 0.0172. And so what that means is that if I were to take a lot of random samples of 799 teens and 2,253 adults, so I have to keep the sampling process the same. So if I were to take many random samples of 799 teens and 2,253 adults, the difference in the sample proportions, because that's what we're talking about right here, is our sample proportions. So the difference in those sample proportions of teens and adults who use social networking sites, so put our context in there, will typically be 0.0172 from the true difference of proportions of all teens and adults, so the whole population who use social networking sites. So again, our standard error is just applying to the samples. So if we're to take a lot of these same random samples, 799 teens, 2,253 adults, the difference in the sample proportion of teens and adults who use social networking sites will typically be 0.0172 from the true difference of proportions of all, so the whole population, teens and adults who use, U.S. teens and adults who use social networking sites. So part B now has us constructing and interpreting a 95% confidence interval for the difference between the proportion of all U.S. teens and adults who use social networking sites. Our problems get a little bit longer now that we have with the 2 samples, because we have to make sure that we address both of them. So in our first part, in our state part, we have to define both of our parameters. So we have to define P1 as the proportion of U.S., because we're only talking about U.S. teens here, of U.S. teens who use social networking sites. Who use social, and then we're going to try to speed this up so I may not write as much. Who use social networking sites. But then I need to define my other parameter. So I need to define P2, which is my proportion of U.S. adults, and I would need to put my context in here, who use social networking sites. And then I need to say what I want to do. So I've got my 2 parameters I need to define. P1 being my proportion of U.S. teens who use social networking sites. P2 being my proportion of U.S. adults who use social networking sites. I know I didn't write it down. Okay. And then we need to say what we want to do. So this is, I'm constructing a confidence interval. I'm not doing a significance test. So if I'm doing a confidence interval, I'm trying to estimate the true difference. So I need to state that I want to estimate the difference of P1 minus P2. The difference of P1 minus P2, and I want to do that at a 95% confidence level. So I need to state that part as well. Okay, and so that would be the statement part of my test, of my method. So I need to be sure I'm defining both parameters as well as stating what it is I want to estimate and at what confidence level. And so now I'm going to move on to my plan part. So in the plan part, I need to be sure that I've stated what test it is that I'm going to use. So I'm going to use a 2 sample Z interval for a difference between proportions if my conditions are met. And again, I need to make sure that both samples meet my conditions. So my conditions are the same as before, random, and it was a random sample of teens and a random sample of U.S. adults. So I would state that random was met because both of my teens and adults were random samples. As for my 10%, I need to check my teens, right? So my sample, and we have a bigger U.S. population than 7,990 teens. And for U.S. adults, I have a bigger population than 22,530 U.S. adults. So I meet my 10%. And then I need to check my large counts. Okay, so when I go to check my large counts, then I need to also again do it for both samples. So I need to do my teens at 799 times 0.8. And these need to be whole numbers, so I'd round down to 639. And then 799 times 1 minus 0.8, so 0.2, which again I need a whole number, so I'm going to say about 160. Either way, we're greater than 10. Okay, and then I need to make sure I do that for my adults. Okay, so 2,253 times 0.69. I'm going to get a whole number here, and then 2,253 times 0.31 with a whole number of 698. All of these things are greater than or equal to 10, so I can move on to the do step. So for the do step, I need to show my critical value, right? I need to show my critical value. Remember my critical value, my Z with the asterisk, right, is 196 for my 95% confidence level. Okay, and then I need to go ahead and I could go ahead and use my formula of my test statistic, so 0.8 minus 0.69 here. So I can go ahead and I can have 0.8 minus 0.69 plus or minus my critical value of 1.96 times all those standard errors, which is going to give me a confidence interval of 0.076 to 0.144. Or I can go ahead and do that on the calculator. And so we'll look real quick on how to do this on the calculator. So if you choose to do this on the calculator, you're going to go to Stat. So Stat, Test, and then 2 prop Z interval. My arrow went right over the name of your test. And I can't move it. Okay, so 2 prop Z interval. You can see the title of it right there. Okay, and then you're going to need to, when you put this into your calculator, you can't put in the proportion. Like for teens, it was 0.8. I need to figure out what number of teens gives me 0.8. So this goes back to doing your large counts condition. You can pull that 639 comes straight from your large counts. Okay, 799 times 0.8. And then you put your sample size of teens. And then you switch over to your other one, which is your 1,555. is my 0.6, my 69% of 2,253, and then my sample of adults. I make sure my confidence level is at 0.95, not 95, but 0.95. And then once I hit calculate, this is what I'm going to get here. And there's my confidence interval right there on the top. Okay, you can see my p hat 1 and my p hat 2 match what I was given. Okay, and I've got that confidence interval on the top. And you can do that on your calculator. You just need to be sure that you lay things out, right? That you write down what test you use, that you use the 2 prop z interval when you went to your calculator. Okay, you need to let them know that, so that you use the 2 prop z interval. You need to write down what your critical value was. You need to give the actual interval on there. Okay, but you can do this as an option, and you'll notice where you pulled this from on the stat and test. You can also do a 1 prop z interval. You can do a 1 prop t. You can do you can do a t interval. So you can do all of these things that we've been doing. You can do them on your calculator. And then your final step, you would need to be sure that you go ahead and you do your conclude part. So for our conclusion here, we need to actually interpret the confidence interval. And it's the same interpretation as it was before. We are 95% confident, okay, that the interval and I'm going to go ahead and use the one that is hand calculated versus the one on the calculator because I don't remember what it is. So 0.076 to 0.144 captures, and here's my slight difference, the true difference, so we never said that before, the true difference in the proportion of all, and now I'm running out of room, of all U.S. teens and adults, so I keep it in that same order of teens and adults who use social networking sites. So not really any different than it was before. Same with a significance test that you'll see in just a minute. It's not really different. So for a significance test, I still need to state a null and alternative hypothesis. Okay, so let's look at this example. Researchers designed a survey to compare the proportions of children who come to school without eating breakfast in 2 low-income elementary schools. An SRS of 80 students from School 1 found that 19 had not eaten breakfast. At School 2, an SRS of 150 students included 26 who had not eaten breakfast. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportions? So I need both a null and an alternative hypothesis, and I would define my parameters just like I would in the state portion of doing the significance test. So my null hypothesis here, I have 2 options. Okay, so my null hypothesis can either be written as P1 minus P2 equals 0. So they have no difference between the two. Okay? Or I can do that my null hypothesis is that P1 equals P2. That would be no difference, right? I have the same proportion of kids that show up at School 1 that didn't eat breakfast as I have at School 2. My alternative hypothesis here is going to be whatever kind of difference that I expect to happen here. And so in this case, I didn't state that I thought that one school had a bigger or smaller difference than the other. So my alternative hypothesis here would just be that the one school minus the second school, so the differences between the two, does not equal 0. And I would need to define my stuff, right? So I have all this information, and let's scoot this up some so I can write. Okay. So my null hypothesis is that the two are equal. My alternative is that they do not equal, where, and then I define my parameters, where P1 is the true proportions of students at school 1 who did not eat breakfast. So where P1 is the true proportion of students at school 1 who did not eat breakfast. And then I would continue on then to say that P2 equals the true proportion of students at school 2 that did not eat breakfast. So I go ahead and I define my parameters here as well. My conditions for a significance test are the same as they were before, same as they were for the confidence interval. Okay, I need to check that both either are from 2 independent random samples or from 2 groups of a randomized experiment. I've got to meet my 10% conditions for both as well as large counts for both of them. Okay, so let's look at the thing that's different here, and that is calculating that test statistic. Okay, so remember we have to calculate the test statistic when we are, I can't spell statistic. We have to calculate that test statistic when we are doing these significance tests. And so when we calculate our test statistic, remember that is our statistic minus the parameter. So our statistic in this case is our sample proportion differences minus the parameter, okay, which is that there is no difference here, over the standard deviation of our statistic. Right, the standard deviation of the stat. And that would equal our test statistic for this particular example. So if my null hypothesis is that the true difference between the 2 parameters is that they are exactly the same, then I need to what I'm going to do is I'm going to end up combining the data from the 2 samples to get a pooled combined sample proportion. Because remember, I think there's no difference between the 2. So if there's no difference between the 2, then I should be able to just pool this into one larger sample. So if you're looking at this school example here, you can see this little table here shows how it would be pooled into one large sample. How many kids from each school ate breakfast, and then we've got our totals from the 2 schools versus how many said yes and no to breakfast. And when I pool these into these 2 samples here, I can then use this formula here. And so this is our pooled or combined sample proportion. That's why it's the P hat C. So it's the pooled or combined sample proportion. And so basically I just took the number of successes in both. So in this case a success was them not eating breakfast. So the number of successes in both, so my 45, okay, over my number of individuals, my complete sample size. So my complete sample size here is 230. So I've got my 230 down there at the bottom. So I have, in this particular example, I have 45 over 230, which gives me a 0.1957. That value is what I'm going to use to calculate the standard deviation of the statistic. Okay, I'm going to use that value in both samples in place of P1 and P2 in both of the samples for the denominator. Okay, so what that looks like is, move some of this. What that looks like is this right here. Okay, so I use my samples up here in the numerator. Okay, so I use my actual samples up in the numerator there, but in my denominator here, you'll notice I'm not using my samples. I'm using that pooled or combined proportion here. Okay, and so that will give us, if our large counts are met, that will give us a Z statistic that has approximately the standard normal distribution when the null hypothesis is true. And we want that normal distribution to be able to put this into our calculator and to be able to use that normal curve there. So we have to make sure our large counts are met, and then again that will yield a z-statistic that has approximately the standard normal distribution when the null hypothesis is true. So this one here just summarizes, reminding you that when you're using your two-sample z-test, if supposing the conditions are met, okay, I'm going to test that null hypothesis, I need to find that pooled proportion in both combined samples before I can compute the z-statistic. And then remember, when I'm finding my p-value, okay, I need to pay attention to my alternative hypothesis to determine whether I'm using a greater than, and so I want this probability, whether I'm using a less than, so I want the left end of the tail, or whether I'm using a do not equal, and I need to make sure I double that p-value. Okay, so looking at this is the exact same example, but it's just taking us all the way through. I'm not going to rewrite some of the stuff that we've already done. So again, it's our four-step process. Our statement part, we already did. We did our null hypothesis, right? Our null hypothesis of P1 minus P2 is equal to 0. We had an alternative hypothesis where P1 minus P2 did not equal 0. And then we went ahead and defined our parameters, where P1 is the true proportion of students at school 1 who did not eat breakfast, and P2 is the true proportion of students at school 2 who did not eat breakfast. My planning part for this, okay, so my step 2, my planning part, I need to make sure I identify my method, right? And so my methods is, I'm going to do a 2-sample z-test for P1 minus P2. If my conditions are met, I've got my same conditions I've had. Random, I need to make sure that both samples are random or from a randomized experiment. Both of them are from an SRS. I need to do my 10%. It told me that both schools have more than 1,500 students that attend each school. So when I do 10 times 80, I get 800, which is less. Okay, and then I also, when I do my 10 times 150, I get 1,500 students. 10 times 150, but it told me that I had more than 1,500 students. So I'm good there. And then I also need to do my large counts, right? I need to do my N1 times P1, which is 19, my N1 times 1 minus P1, which is 61. And then I need to do it for the second sample as well, right? N2 times P2, which is 26. And N2 times 1 minus P2, which is 124. That's a 4. All of these are greater than or equal to 10, so I meet these large count conditions. So I'm good there. Now I need to move on to the do part. And so in the do part, this is where I get a couple of things that are a little bit different, a little bit new here. So I need to make sure that I go ahead and I calculate that combined proportion. So we had calculated this before when we were talking about what this meant. Okay, that 19 plus 26, all my successes over my total sample size, and I get this 0.1957 for that. Okay, and then I need to go ahead and I need to calculate my test statistic, okay, which is going to be p hat 1 minus p hat 2, which is 19 over, that sample had 80, 19 over 80 minus 26 over 150, okay, minus my parameter, which was 0, that there was no difference, right? And then when I calculate my standard deviation for this, I'm using this this combined value. So 0.1957 times 1 minus 0.1957 over my sample size of 80, and I use this for both samples. So 0.1957 times 1 minus 0.1957 over, again, my sample size this time of 150. And this is going to give me a test statistic of 1.17. Okay, so I can either use my normal CDF on my calculator. So let me give me some space here, which I know that most of you guys do. Okay, so you could use your table, or you could use your normal CDF on your calculator. This time, though, I want 2 times the probability that Z is greater than 1.17. I used greater than because this is a positive Z-score, and I think that was maybe some confusion in the last chapter. Okay, but when it's a negative, go ahead and use less than. When it's a positive, go ahead and use the greater than. And I'm going to go ahead and calculate that because I'm using a greater than. This is 2 times 1 minus whatever that value is I get, which is 0.8790. And it's a 2 times, right? It's a 2 times because it was a did not equal alternative hypothesis. Or I could do this on technology. And so, again, I think for these, it's going to be easier to do it on your technology. Okay, and so when you're doing this on technology, you're going to go to what you did before. You're going to go to the stats, and you're going to go to test. So stats, test, a 2-prop Z test. So again, this time I went to a 2-prop Z test instead of a 2-prop Z interval. Okay, again, I need to put in my whole numbers here, not any kind of proportion for each sample. This time I had a did not equal alternative hypothesis, and then I'm going to go ahead and hit calculate. And when I hit calculate, that'll give me my Z-score, my my test statistic. So this will give me my test statistic. It'll give me my p-value. Okay, remember though, don't lose sight of being able to interpret those, and you've got to make sure that you write both of these down in the do section. You need to say that you use your technology and the name of the function on the technology, and you need to say what your test statistic and what your p-value is, and be prepared to interpret them if you have to. You can also select the draw button here instead of calculate, and it will show you what it's doing. Okay, it will show you, it will give you your test statistic and your p-value, and it will show you that you were getting the probability under the 2 ends of the curve there. And then you're going to need to move on to your step 4, which is your conclusion here. Okay, and so you're going to need to do your conclude, your interpretation, because, and this is the same as it was before, because our p-value of 0.2427 is greater than alpha equals 0.05, we fail to reject. This is pretty likely to happen, okay, not necessarily just by random chance. We fail to reject my null hypothesis. There is not convincing evidence that the true, we got to put that word true in there, that my true proportions of students at the 2 schools who, true proportions of students at the 2 schools, and I'm out of room, at the 2 schools that don't eat breakfast or that didn't eat breakfast is different. Okay, that the true proportions of students at the 2 schools that didn't eat breakfast is different. Make sure, again, you put that context in there. Okay, so I know this has been long, but we're going to do one more thing. What if this was a test and an experiment? Okay, essentially it is exactly the same. With an experiment, you do not have to check your 10% conditions if you're not doing, because you're not randomly selecting from everybody in the population, people volunteer for an experiment, you do not have to check your 10% conditions here. Okay, so go ahead and take a second and pause it and read about your experiment, and then you would perform it in the exact same way in that 4-step process. So in that 4-step process, we're going to do our state part, again, our plan, our do, and our conclude. And I'm just going to run through parts of this so that this doesn't get any longer. If you want to see every single bit of this worked out for you, this is going to be on pages 625 and 626 in your book. So in my state part, I need to be sure that I'm stating my null and alternative hypothesis. So I can either, remember, I can either state this as P1 minus P2 equals 0, or that the two are equivalent. You do not have to do both of them, though. My alternative hypothesis in this one is going to be that my difference in the two is less than 0. Okay, and that my difference in the two is less than 0, because I'm hoping that this drug is better than no drug. Okay, and I'm going to put all my context in there. I'm going to define these. P1 is my actual heart attack rate for middle-aged men like the ones in this study. Can't apply it to all middle-aged men because these were particular middle-aged men. They were a certain age. They were in certain other health conditions. So that doesn't apply to every single middle-aged man. So like the ones in this study who take Gemfibrozil, and P2 is the actual heart attack rate for middle-aged men like the ones in this study who only take a placebo. So what they're trying to prove here is that the drug is better than the placebo. Okay, and so I could have, if I wrote, depending upon how I wrote these hypotheses, if I use this first null hypothesis, I need to use this one. If I wrote that the two were equivalent to one another, then basically I want to write that the drug is better than the placebo. Okay, there's a lower rate of heart attack. And then again, I also need to mention my alpha. And you'll notice that your alpha here, it's a pretty small alpha because this is a drug. I don't want to say that this drug works and it doesn't. Okay, so I want to be pretty careful with something like this. Okay, as for my plan, I do the same thing I always do. I would state my method, which is that I'm using my 2-sample z-test for P1 minus P2. I do my conditions, random and large counts. I don't need to do 10% because I'm not sampling here. Okay, and then for my do, I can move on to, I could go ahead and use the calculator. Remember, I'm going to need to do that p hat combined here. Okay, and so when I find that p hat combined, I'm going to need to use that to calculate my test statistic, or I could go straight to my technology. I can go straight to my technology, and I can pull that information off of the technology. One of the things that I think you may need to do is, even if you go straight to the technology, you don't need this in the technology. You don't have to enter that p hat combined value, but I think you still need to show it, and it will show it to you in your technology. Let me pull that picture up again real quick. So in your technology here, you will see that you get this third p hat value right here, which is your p hat combined. Okay, so it will give it to you. You just need to know what your calculator is giving you. Okay, and so then after you have put that into your technology, you're given a z equals negative 2.47. You have a p hat combined of 0.0343. You have a p value of 0.0068. So make sure you list all of those things, and you say the name of the technology that you use, the 2-prop-z test on your calculator. And then you would move on to your conclusion there. Okay, because my p-value of 0.0068, okay, is less than 0.01, we can reject the null hypothesis. There is convincing evidence the results are statistically significant at the alpha equals 0.01 level. There is convincing evidence of a lower heart attack rate for middle-aged men like these who take Gemfibrozil than those who only take a placebo. Sorry for the long one, but I think this will give us extra days to practice this stuff that you already know how to do with just a few tweaks here and there.